Hello everybody and welcome to the online certification course on microelectronics devices and circuits. Now in this lecture module we will be actually looking into BJT as an amplifier, and then we will be also looking at BJT from small signal model point of view. Let me recapitulate what we did in our previous lectures. We had looked into bipolar transistor, the structure of that, both NPN and PNP, what are the relative doping concentrations of the emitter, base and collector, and what should be the size of each of the regions of the BJT for the most optimized functioning of the BJT. We have also seen the various electrical characteristics of the BJT, and we have tried to ascertain the fact that how can you bias your emitter base and base collector junction, and we have seen that depending on that there are 4 modes of operation. So I can use BJT in analog domain for the purpose of amplification when you are actually biasing it in the forward active mode, right. You can also make it into cutoff provided both your emitter base and base collector junctions are reversed biased, right. So we will learn 2 things, very important things in our by the previous discussion which we had, and these 2 things are: the first thing is that BJT can be used as a, of course, as a switch, right. So we can go from on to off state, right. How can we go from on to off state? This is again active forward, right, active forward state. So what will happen in this state? Your EBJ, emitter base junction, will be forward biased, and base collector junction will be always reversed biased, right. So you have an on state. What is the off state? Both EBJ, emitter base junction, and base collector junction both will be reverse biased. In that case it will be off state, right. So I can use BJT as a switch for sure, and therefore whenever you require a heavy switching action, BJT can be used, and it is a very fast switch, understand it to be very fast. The only problem with BJT switch is that when you go from on to off state and you want to change the biasing, you actually have to change the biasing of the EBJ from FB to RB. So EBJ has to be changed, and therefore we have to be very cautious that how fast this changes. The more fast this changes, more higher frequency, at a much higher frequency the switching can occur, right. So that is what we need to look into. We have also learned, second thing is that since BJT is able to convert small currents into large currents, it can be also used as an amplifier, right. We have seen that in our previous discussion. So 2 things are clear at this stage, that a bipolar transistor can be used as a switch as well as an amplifier. One thing which we have left in our previous discussion is the name bipolar. Why is it known as a bipolar transistor, junction transistor? And the reason is very simple, because in both NPN and PNP we use both electrons as well as holes for carriers, as carriers, right. They use both electrons and holes. So both electron and hole current is responsible for the total collector current. So the total collector current which you see is actually a function of the number of electrons as well as number of holes. Why number of holes? In an NPN transistor, for example, why number of holes? Because if the number of electrons are high, of course your emitter current will be high, but if your number of holes are also high, then the probability of recombination in the base region, right, recombination will also be high, right, and as a result your collector current will be smaller now, which means that if your hole concentration is large as compared to the previous case, I would expect to see my collector current to slightly drop down as compared to the previous case, and therefore bipolar technology or bipolar transistor, as the name suggests, will have contribution from both the carriers, electrons as well as hole, right, and therefore we define that to be as a bipolar junction transistor, and that was the name which was given to it way back in 50s when it was actually found out, right, fine. So we have understood the origin of BJT. We have also understood that BJT can be working as a switch. We have understood the working principles of an NPN and a PNP transistor. We have also understood the biasing criteria for the BJT to work fine. So let us now therefore switch our attention to BJT as an amplifier. That is the first thing which we will be learning. So, let us just have an outline of the talk which we will be going through in this series of lecture. We will be looking at BJT as an amplifier first of all. So, given a small signal peak to peak, how can I increase it to a large signal, right. So, that is what we will be learning in this lecture, that given a peak to peak small semester, should I get a BJT as an amplifier, I can get a large this thing. We will be also looking therefore about the biasing criteria of the BJT, right, because this is quite important, very important section, and the reason is you can have an amplification at any one point of time, but ideally your amplification should be independent, or voltage amplification should be actually independent of the input voltage, right. So, where you bias your input voltage where is your input voltage should not determine the value of your voltage gain AV, right. So, that is, please be careful. So, therefore, if the BJT has to be used ideally as an amplifier, then it does not matter to me per se that whether you are giving a signal A1 sin omega t or you are giving a signal A2 sin omega 2t and so on and so forth. As long as these signals are small signals, right, and we will see that later on, I would expect to see that I would get almost a linear amplification. Linear amplification primarily means that there is a linear profiling between the amplification and the input voltages, right. Now, to do that, we should therefore learn, which is the second case, that how will you bias your circuit in a manner, right, and to obtain a linear amplification, right. Then we will therefore learn that how to determine the voltage transfer characteristics by graphical analysis, right. What is the meaning of voltage transfer characteristics? As we will see, it is output voltage on the y axis and V out, and on the input axis, on the x axis we have V in. So, how does V out versus V in vary, right. So, if you vary V in, how does V out versus V in vary, right, and we therefore need to find out AV as del V out upon del V in, right. So, that is what we get as the voltage gain or the amplifier gain. That is what I was talking about in the fourth part of our lecture. In that amplifier gain will be discussed, and on what factors does the amplifier gain depend, we will be looking into it. Now, in most of the cases, these BJT or bipolar transistors as the name does not in a sense work standalone, right. You have to use this in circuit analysis. So, you have to sort of take this BJT and plug it and play it over a circuit for example, right. So, what people have done over the years is, rather than therefore every time discussing the device behavior, if we are able to have a circuit representation of a BJT, right, a circuit representation, then every time we encounter a BJT we replace it by its equivalent circuit. That is what we will be learning when we discuss small signal model, hybrid pi model and T model. So, these are the two models which we will be learning. In these two models we will be able to therefore, given any BJT in any configuration, see common emitter, common base or common collector, I will be able to give you a corresponding circuit model for that, which can be plugged and played within any of the BJT configurations for better understanding. We will be again looking into, we will be revisiting again the common emitter, right, common base and common collector amplifier, and we will be looking with how does it vary when you have an emitter resistance being applied here, right. So, please remember yesterday's talk when we were discussing common emitter, there was no emitter resistance. So, what we did in our previous turn was that we were something like this, that it was grounded, right, and this was RC and this was VCC and this was RB, right, and this was applying a base and so on and so forth. So, this was my BJT, and my emitter, which is this one, was totally grounded. We did not apply any potential here, right, there was no resistance between the ground and the emitter node of the BJT, right. We will like to see how inserting a particular resistance in the BJT in that particular emitter node, how does it influence the overall capability of the common emitter configuration. So, these things we will be watching as we, and then finally we will recapitulate what we studied across this lecture series, right. So, this is what we will be looking into. The first thing will be that BJT is an amplifier. Well, as I discussed with you, the BJT will act as an active amplifier only in the active mode, right. It will also act in it will also act as amplifier in other mode, but that amplification will not be a linear amplification, and therefore, my del V out del V in, which is basically the voltage gain, might be a function of V in, right, or V out, in a sense that if V in therefore varies, my AV will vary, and therefore, that is not a good idea. In reality, you should be very careful that voltage gain should not be a function of V in or even V out. It is not a V out, but surely not a V in, right. So, this criteria has to be held very confirmed or in a very careful manner, that the voltage gain should not be a function of V in and V out, right, and that is quite important, or an important observation to take care of, that typically they should be holding no functionality in terms of V in and V out. Now, as we have seen therefore, that BJP therefore acts as a voltage controlled current source. Why? This is basically voltage controlled current source. So, if you remember, we have 4 types of sources. One is known as voltage controlled current source, current controlled current source, right. You have a voltage controlled voltage source, and you have a voltage controlled current source, right. Sorry, so you have voltage controlled current source, you have current controlled current source, you have voltage controlled voltage source, and you have a current controlled voltage source, current controlled voltage source, right. So, there are 4 types of sources which is generally available to any electronic designer, right, and an example of current controlled current source is basically a BJT, right. A MOSFET, for example, is a voltage controlled current source. So, a MOS device we generally get. Think about these two yourselves and you can get one example of BJT is also a voltage controlled current, it is also voltage controlled current source just like BJT. We will see that later on, but primarily BJT is a current controlled current source, and therefore, it is basically a because the current in the base side of a BJT will determine how much amount of current there is in the collector side. Therefore, we define that to be as a CCCS domain as far as BJT is concerned, right. So, these 3 things you should be very careful that these are 4 sources, right, and these 4 sources are all dependent sources. Let us assuming that these are all independent sources, but each source is having an external bias, right, external bias. So, all of the sources are having external bias, but they are of independent nature, right. So, this is what we will be learning as we move along, and therefore, what we have learned just now therefore is that the change in the base emitter voltage, which is this one, gives rise to a change in the collector current IC. I think this has been already discussed to a larger extent. So, if you make your, for example, if you are using a silicon transistor and your VBE is less than 0.7, you can be amply sure that the emitter base junction is cut off, and therefore, there is no current, appreciable amount of current flowing through the emitter base junction. So, your device will be in off state in that case, because you are not allowing any of the transistors to, any of the electrons to flow in case of an NPN transistor, the majority current carriers you are not allowing it to flow. But once your base to emitter voltage exceeds 0.7 in case of silicon, which is the cut in voltage, I would expect to see an exponential rise in the current by varying a VBE, right. So, if you vary VBE near the knee point of the PN junction, then I would expect to see a large amount of current flowing through the collector side once the input voltage is larger than the cut in voltage or 0.7 in case of silicon. As I discussed with you, therefore, the active mode of BJT can be used to implement a transconductance amplifier. Forget about this word transconductance, we will be looking into it in a detailed manner. But you know, you must be remembering what is transconductance. Transconductance is defined as GM, transconductance. GM is defined as del ID del VGS, right. It is del ID del VGS, which means that it is basically rate of change of drain current with the rate of change of gate to source voltage, right. That is what is GM. Now therefore, what is a transconductance amplifier? Transconductance amplifier is an amplifier which amplifies the output current because of the change in the input voltage. So this is your input voltage, right, V in. So there is a del of V in here, because of which there will be a change in the output current del ID, and division of that is basically my GM, transconductance, right, and therefore it is also referred to as a transconductance amplifier, right. So we refer to this as a transconductance amplifier, and that is quite an interesting topic which people have been dealing with when they are dealing with these BJTs or bipolar technology. Now therefore, so that is what I was saying, that so the last point is that the voltage amplification, right, can be obtained simply by passing the collector current through a series resistance RC. So you have IC available with you because of a collector current is available with you. Now if the collector current you are forcing it to pass it through a resistance RC, then ICRC is basically the drop of the output voltage, right. Now even if your input voltage is small and output voltage is large, your AV will be therefore typically very high, of the order of maybe 100, 200, 300 and so on and so forth, right, also referred to as a voltage gain in this case. So two things we take away from this slide: BJT should be in active mode, or a bipolar transistor BJT should be in a active mode if it wants to act as an amplifier. Changes in the value of VBE will give rise to a change in the value of IC. The third thing is that it is also referred to as a transconductance amplifier, because the input is basically a voltage and the output is basically a current, and the amplification can be thought of as the output current passing through the resistance RC. The voltage drop across that resistance is defined as my voltage, output voltage, right, and the division of output voltage to input voltage is therefore referred to as a voltage gain, right. Okay. Let me come to the next slide and show to you how biasing of a BJT can be used to obtain a linear amplification, right, and we will see step by step each one of them in a much more detailed manner. Now if you look at this left hand side figure, which is this one, right, if you look at the left hand side figure here, right, left hand side figure here, I have an NPN transistor which is marked by this red circle, let us suppose, right, and what we get is that we bias it by an external source VBE, and we have IC and VCE, right. Now the obvious question, how do you physically amplify? When you amplify any signal, how do you do that physically? Well, first of all you apply a DC bias, right, you apply a DC bias onto the device itself, which you are supposed to amplify. Once the DC bias is applied, you need to superimpose the small signal model over the DC bias in order to sustain a output voltage variation, right. So I therefore mark my DC level, and superimposed on that I have an AC cycle available with me, that multiplied by AV voltage gain gives me the output for any BJT. Now that will come later on. Let us see what are the functionalities of linear amplification. Now if you look at this figure here, when VBE is less than 0.6 or 0.7 volts, which is on this side somewhere here, right, the value of the device is cut off, right, the device is cut off. So when the device is cut off, automatically all the VCC will fall across the output voltage, and that is what is happening. So the output voltage you have got VCC and remains VCC up till a point Y, where what is happening, where you will have the institute amplification to be 0 in that case. So the amplification will start after point Y, but from the point of view of operation we say that till Y, or till let us suppose Y on this axis and say x1 on the VBE scale, right, I can safely assume that the device is in the off state and therefore output is at VCC. Agreed? When my therefore voltage crosses 0.7, right, it switches on my transistor here. As a result, the voltage at this point starts to fall to VDD, and that is sorry at threshold at the 0 bias, and then something happens here. We define a point which is known as the Q point or the bias point, where you need to sustain or you need to keep your device there in order to ensure that the device is in linear amplification mode, and I will explain to you why is it like that. See, if you look very carefully, Y and Z are the 2 points at the 2 extremes after which the voltage VCE is almost independent of VBE. It is a straight line before Y and after Z, actually after Z people have not drawn, but after Z it looks something like this. It is almost a straight line, right. In both the cases before Y and Z, right, before Y and Z, we expect to see that the current the voltage is constant, right, voltage is constant, and then after Y the output voltage starts to fall down, and you know the reason why, because after after input voltage has crossed the value of your on condition, this tries to switch off this M1. As it tries to switch off this M1, more and more current will flow, and you will expect to see this to fall down, and when a time will come when this goes off or almost very near to 0, then this will result in this point, which is the starting point, to be actually elevated to a high value of voltage, and that is what is happening here. So, as you make your Y1 move slightly higher, there is a certain drop in the voltage, and the reason is, in that case the device is in the on state, and therefore when the device is in the on state, it pulls all the extra charge carriers towards its center, leaving it neutral charges. That did not happen, and therefore what will happen is at point Y I would expect to see that the output voltage is latched to VCC. Now, if you input an active voltage both active, so in fact it is VCE which is latched to 88 to a high value of VCC. Now, you see we define the Q point, quiescent point, to be Q as quiescent is referred to as quiescent point or a point which is highly stable point, right. So, these two are the definitions of the Q point which is seen in front of you, and which means that this Q point by application of an external bias can move up and down, but within the linear regions of amplification process, right, and that you should be very careful as far as designing is concerned, that you cannot let the Q move anywhere it likes, but only across the small signal domain, right, and such that you get a large amplification in this area. Now, if you see very carefully, as the voltage exceeds Z, right, input voltage exceeds Z, that ensures that this device is basically your cutoff. So, VBE is very large primarily means that your cutoff has taken place, and the voltage actually goes down to almost a 0 value, right. What is left for you to understand therefore is how does your Q point behave, which is this point. This is also referred to as a quiescent point. How does it behave and how does it help us in averting any problem? See, if you look very carefully, if your device is biased here or here, you are either in input state 0. So, this is input state 0, or you have got here input a large input, fine. So, a large input and a small input, I can show it on the same graph, and this is how it is done. Before we show you how it is done, we will just comment on the fact that the points between Y and Z, right, are so small space between each other that they seem to merge with each other, right, but there are sufficient number of points to evaluate beyond Z and Y that this region is the highly amplification zone, and this region are the basically your digital zone. So, if you want to work in digital electronics or digital domain, you need to work in the region XY and Z to this much point. So, this is a M Z to M, right, and so on and so forth. You do not have to go for all the details which is available in the literature, open literature for this case. You will obviously now typical value of Q is such that it is Q is somewhere around VCC by 2, right. So, whatever is the input voltage or VDD I am using, or whatever clock voltage, I just have to half it when we talk about quiescent characteristics or a low power characteristics. Now, what will happen is that as you, for example, VCE is equal to Q point, as you can see, and the x axis is VBE, right. Now, let me say that therefore, if you want to work in digital domain, XY and ZM are the most logical digital principles, because it is 1 0 and 0 1 here, and this slope gives rise to a constant gain. Are you able to get the picture? Because AV will be equals to del V out by del V in, right. So, it is del V out by del V in, which means that my output voltage will depend, the output voltage will depend upon the input voltage as such, right. Secondly, what about the gain at XY and ZM, because gain is change in the output voltage upon change in the input voltage. So, though your input voltage is changing, output voltage is constant, and therefore, your gain at this point is exactly equals to gain at this point, right. Gain is at this point, fine. So, gains are exactly equal in both the cases, but the gain shows a drastic change in the middle region depending upon how steep the slope is. So, if your slope is very steep, right, something like this, you will have your infinity even an infinity gain shown to you, right, and that is how people work with inverters for static application purposes, right. We now therefore come to determining the VTC by graphical method, right. How will you find out the voltage transfer characteristics by graphically, or looking at a picture at a graphical point of view, right, and that is what is required, and we will discuss that in this section on this lecture, right. Let us take one important point, let us take a BJT switch or a BJT transistor as an amplifier, right. BJT as an amplifier, let us take. Right, BJT is an amplifier. So, what we do is we try to provide the candidate enough database in order to appreciate the working principle. Let us see how it works out. So, if I have a diode connected load, or for that matter any load, right, what I am trying to tell you is that in this case, as you switch on the value of input voltage, and one of them may be AC, you expect to see a large amount of current flowing here, but since it is normally an off state, there will be no current flowing through the inverter, or in this matter CMOS, and therefore, you require a person from inside to switch it on, right. How will you do that? By simply making this BJT work at typically at VBE greater than 0.7 volts. When you make it VB greater than 0.7 volts, you switch on this base emitter junction, and as a result you will get a output is available to you. So, so what was the concept is that in a common emitter mode configuration, let me draw for you the common emitter mode configuration design, right, and this is without the emitter, without the collector or emitter configuration VCC, right. You had RB, and then you had VBB, and then you had this, and then on the emitter side you had this. This is your output, and this is your input, which is basically a sinusoidal input. So, what has happened is that because of this VBB, I will have a current, this VB is here. So, what will happen is that there will be a base current IB, which will be formed by doing VBB minus V let us say EC. So, this is a breakdown voltage. So, we write down IB to be equals to this divided by RB, where RB is the base resistance here, fine. So, you put the value of VCC, you put the value of VBD, put the value of RB and you get IB, right, you get IB. Now, once you get IB, you need to multiply that with beta in order to get IC, right, and this beta is of the order of few hundreds to 200 value, and I get IC, right, I get IC here the collector current. Now, this collector current multiplied by RC gives you the voltage drop across the resistance, right. So, that is what you get as the. So, what is the output? Output is VCC minus ICRC is equals to a V out, fine. So, I get V out to be equals to VCC minus ICRC, right, and I get this quantity here, and therefore, I get IC to be equals to V 0, right. So, VCC by RC, and I will get minus V 0 by RC. So, I get IC to be like this, right, which means that if you look very carefully, or if you look or even if you look at this particular point, I can safely say that this is the final content, that the collector current is only depending on the value of VCC by RC and it depends upon minus 1 by RC VC, which means that if you compare with the fact this is equal to y equals to mx plus c, m is basically your 1 by RC, right. So, with why with the negative sign, because the slope is negative, right. So, if I have something like this, is positive slope, if I have something like this, it is a negative slope. So, since it is line is something like this in the reverse direction, we get a negative slope, and therefore, m is fixed at minus 1 by RC, right. Now, therefore, if you know m, you know x, y, I can get the value of c, right. So, this is the standard methodology which people used. Now, what has happened is over the years, and typically in the early years, we used to find out the VTC or the voltage transfer characteristics by graphical method, fine. So, we will do that in the next turn. Today we have learned the basic idea of a short circuit or a small signal model. Next turn we will be learning how to find out the voltage transfer characteristics by graphical analysis. A detailed analysis will be followed. Okay. Thank you very much.